Hi everyone and welcome back to Digital Design with Verilog course. So today we will discuss about event control and data types. So let's first start with event control. In the previous lecture I gave you a bit of glimpse about event control, like we use these kind of statements. If you remember, there was a statement always pause edge negate. Okay, now what does this pause edge and negate actually mean? Although I told you that this means the positive edge of the reset, this means the negative edge of the clock, but today we'll understand it in more in-depth manner. So event control in Verilog allows you to specify when a block of code should execute based on changes in the signal. This can be done using two ways. One is the edge triggered, other one is the level triggered. Okay, so first we will understand the edge triggered, then we'll understand the level triggered. Okay, so like you basic things you know, right? Edge triggered clock. Okay, then positive edge triggered clock, negative edge triggered clock. I hope you have studied that in digital electronics. We have, like, if you remember, we had a, like, let's say D flip flop like this. Okay, then I had a like sign like this, symbol like this. Okay, this if I rotate and this if I take it here. So if I have a sign like this, right, then by default you understand this is a positive edge clock. If I have a circle around it, okay, if a small circle around it, then you, like, if a bubble around it, then you tell this is a negative edge trigger, right? So like that is what we try to simulate in Verilog as well. Okay, so here what we observe is edge triggered means edge triggered event control makes the execution of a block, like execution means that always block, or any other block also. If there is some condition, we will understand in different use cases or as well. For now, just understand we are using event control in always block. We will use event control in other blocks as well. We will see those possibilities. Okay, for now just understand we are using it in always block. Okay, so makes the execution of a block dependent on the rising, positive or falling edge of a signal, typically used in clock driven behavior or sometimes in resets as well. Okay, positive edge, as the name suggests, is triggered when the signal changes from low to high. And in Verilog, how do I define positive edge? We write pause edge. Okay, that is what we write. And negative edge means triggered when the signal changes from high to low, goes from 1 to 0, and in Verilog we define it as neg edge. Okay, so these are the different possibilities which can cause negative edge or positive edge, remember. Okay, so if my initial signal, like let's say example for clock, if my initially clock was 1 and it went to unknown, then this neg edge will actually trigger, this will get activated. If my initial signal was 1 to Z, it will obviously get activated. 1 to 0, it will obviously get activated. X to 0, then also it will get activated. Z, high impedance to 0, then also it will get activated. So these many are the possibilities. Okay. So only which is left, which is not possible, anything going from 0 to anything, right? Anything going from 0, the negative edge ignores that. Okay, negative edge ignores that. Okay, anything going from 0 to any question mark, right? Negative word doesn't care about that. But anything going from 1 to any other value, the negative edge will trigger the block. Okay, same for positive edge, just the opposite. Anything going from 0 to any value, 0 to any value, right? Or x to 1, like unknown to high, high impedance to high, or 0 to any value, it will trigger, pause edge will trigger. Okay, so I hope you understood these points. When will negate and pause edge trigger? This one you have to take care of. This one you should be, like, at least like understand this conceptually. Okay, now let's understand, this is about the positive edge and negative edge. Now let's understand the level triggered event. So level triggered event control makes the execution of a block dependent on the level value of the signal rather than its edge. So it doesn't not care if my signal, right, is like going from low to high or high to low. It does not care about that. Okay, it just cares that if my signal is changing any value, if my signal value is changing, that means I will execute this block. This block will be executed. So the block is triggered whenever any of the specified signal changes. Anything changes here, the block will be executed. Level control or combination of signals can be triggered by any change in a signal in the list. Okay, in the sensitivity list. This is known as sensitivity list. Okay, so basically this block here, if I write there, when will this block will be executed? This block or statement will be executed only when A or B changes. Okay, then only this block will get executed, else they will not get executed. Okay, so let's give you a bit of examples. If I can go back to my code, and do I have any examples here of triggering? I don't think I have made any like code for this, because I didn't feel the codes were that much important here. Yeah, actually the codes were not that important. Just like I wanted to explain the triggering and all those things. I don't think we have to go to the code and see this. I think whatever I've explained, this should be enough. Okay, now I will come to like a one more design in Verilog to understand whatever we've learned in a better manner is mux design. Okay, so don't worry, we will design this mux again later on. Okay, don't worry about it. Just now I wanted to give you a feel of whatever we learned to implement that. Okay, so this is the gate level description of a mux design. So a mux, like 4:1 mux is like this, right? Although I have discussed about 4:1 mux using 2:1 mux, but now we are directly implementing the gate level description. Okay, so this is a 4:1 mux where I am getting the output, and like circuit diagram, I hope I don't have to explain to you guys. S0, S1 is there and signal lines, and that's how the circuit diagram is. So I will implement the same in the Verilog code. Okay, implement the same in the Verilog code itself. So here I have two NOT gates for this S1 and S2, as there you can see not S1 not S2. I am getting the signal, and those I am feeding it to some AND gates, and the ultimately I am doing the OR after this. Okay, so this is the Verilog code for a mux design. What you should know is you should understand how am I interconnecting the blocks. Okay, so this is the input and this is the output. Generally, like that is the trend. Output will start first, then the input. Okay, so input to this NOT gate is S0, and the output will be obviously not of S0, that is written here. This is a intermediate signal. Okay, so here also not of S1 and S1. So then again this is the Y0. What is Y0? Y0 is the AND of not of S0 and not of S1 and I0. So because like I hope you remember the what do you say? I hope you remember the like 4:1 mux combinational logic. So what was the logic of combinational logic? So if I write the combinational logic of 4:1 mux, it is like S0 S1 I0. This should be something like this. Okay, this should be okay, or S1 bar S0 I1. I hope you know this. I will not explain how am I writing this. This has already been taught. I2 or S1 S0 S3. So not S3, sorry, I3. So I will need this, right? I will need S1 bar S0 bar into I0. That is AND. Okay, so that is what is done here. S1 bar S0 bar I0, and here the second AND gate I1 S1 bar S0, and then in the third gate S1 S0 bar and I2, and same for the other one. There is no NOT here. Okay, so ultimately then what I'm doing the OR of all this, right? OR of all this. So that's why a OR gate has been used, and ultimately the output is stored in Y. Okay, so like just a basic design I am showing you, gate level design. Okay, gate level design. Now I will show you the data flow level. This was the gate level design. We were using gates. Okay, we can use the data flow level. So here what we're doing, this is the data flow level. Don't worry about this operator right now. I will explain this later on as well. Okay, this is just an AND operator. Okay, without using the sorry, without using the gates, how can I call it data flow? Data flow, obviously, if you don't know, there will be a sign statement. Okay, then y will be equals to this, right? This is a blocking assignment. Don't worry, I will talk about this blocking assignment. So what is the difference? What blocking assignment? Don't worry, I will discuss about this. We have a topic later on for this. What is the difference between this and this. So here, right, I am actually specifically saying the intermediate connections, but here I am not saying any intermediate connections, right? I am not saying any intermediate connections. Just what I am saying, how data flows from input to output. That is the main purpose of like explaining this thing, that how is the data flowing from input to output. That is what I wanted to like show in this, okay? But am I telling like this, where will this intermediate node not S1 connected, where will this Y3, Y2, where will I get? No, I did not tell it anything, right? The connections are sorted by the synthesizer itself, okay? So that is the difference between data flow level of modeling and gate level modeling. Okay, this is OR. Don't worry, we have a separate topic for this, like what are these operators. But for now, just like whatever I'm telling you, just understand that this is OR. I'm doing the AND, then doing the OR. Okay, so now let's come to the behavioral level of modeling. So in behavioral level of modeling, again, this is totally different, right? Totally different. We are just it is like a C code. Okay, if you have ever learned about C code, it is just like a similar to C code. Okay, similar to C code. Okay. So this is even different. I'm not even telling it how the data is flowing from output to input. I'm just writing a C code. There are 4 cases. If my select lines are 0, 0, then it will be I0. If my select lines are 0, 1, it will be I1, 1, 0, I2, 1, 1, I3. Okay. Don't worry what is this case statement. Don't worry. All this will be explained later on. Just giving you a idea of the 3 different cases that we have learned. Okay. So this is the sensitivity list. Okay, even if one of them changes, right, this block will be executed. Like let's say if the select line changes, obviously block has to execute. If the inputs changes also, then also block has to execute it, because I0 has changed. So output is showing I0, but it is showing the previous value of I0. I have to update the value of I0. That's why I have to again go and do this, right? And these are all using what? Level trigger. So any value change, they will execute. It is not like edge change. Okay, so that is what I wanted to explain in this. Now let's come to few like topics, few terms that I have been using but I have not explained to you, like display. Okay, so display system task in Verilog is used to print formatted output to the console during simulation. It is widely used for debugging and providing simulation logs. Okay, that is what display is used. So like I have already used display, so I will explain it display a bit more. Display output the message immediately when the simulation time reaches the point of execution. Okay, so it can immediately display whatever I want to write. So if you want to write, like if you want to display anything, any string, okay, on the terminal, then you have to insert that in double quotes. Okay, and let's say if you want to display some variables, like you have chosen, like you have assigned var x, and I want to show this variable on the terminal. How will I show this? Like we have been using that with percentage. Okay, so I will first write percentage. If you write percentage, right, it is a placeholder. That means the Verilog compiler understands that this percentage means whatever will come after this. That means it is a placeholder for anything that I will write after this comma. Okay, after this comma, whatever I will write, it is a placeholder. So after this comma, I write port ID. So instead of this, right, automatically port ID will be replaced. What does this B means? B means in binary. Whatever, like this will be a number, display this number in binary. So that's why port ID is displayed in binary. Okay, if I would have written here D, then the compiler would have understood display this number in decimal. Okay, that is how the compiler would show. Now that is basically it. Simulation time is here. So like we can do many things. We can use the display, and like these variables can be displayed, okay, according to the percentage. So although I have here, if you notice, although I have initialized it with 5, by default we can write decimal, right, it is 5, but here, right, it is displaying the binary. So I can do that. Whichever number system I want to show display to the user, I can do it. I can write here H is for hex. I can write here O is for octal. Okay, so that's totally up to you. Now another one is dollar time. So dollar time, although I have told you previously, like this display, right, is similar to printf function. If you have done C printf function, you will know. So it is similar to that. Okay. Now dollar time, what is dollar time? Dollar time is basically used for displaying time. The current time, if I am at this line, right, what is the time at this point of time? Okay, so I have used dollar time previously as well. You've seen the time is getting used, so it is very useful for knowing like what is the actual time at that particular point. Okay, that is what dollar time is used for. And like how would I show it? So here, right, I will write here this percentage t, and here I will write dollar time, so automatically this time will be displayed here. Okay, line break, if I have backslash n, which I have discussed previously as well, it will insert a new line. If I have backslash t, it will insert a tab. Okay, okay, so yeah, that is basically it. These are all different format codes, okay, placeholders for getting different values. Okay, you can go through this, these are all the values. Okay, so you can use this, you can play around with this. I will not go too much in depth here. So there are two more things, like I have explained this previously as well, that stop and finish, right? So finish terminates the simulation quickly, stop suspends the simulation and enters into debug mode, which we will not use for now. This is not like for our purpose. Mainly we will use finish. Finish means basically terminate the simulation. We are simulating something, right? After, like, let's say if I write here $100, sorry, $100 finish. This basically means, and remember all this, right, all the keywords will be lowercase. I have explained this previously as well. Basically means this, that finish the simulation after 100 units of time. Now 100 units of time, whatever is defined according to you, like we define the time as well, so according to that, whatever we define, after that it will be finished. Okay, so that is what a display finish statement does. Now like I have explained monitor previously as well. Let's understand this in depth. What does a monitor statement do? Okay, so what does monitor do? Monitor is a Verilog system task used to display values of specified signals whenever any signal is in the list changes during the simulation. So display, right, it only executes once. Okay, display only execute once unless we are using some for loop or something. Okay, that is what separate discussion. But monitor is like just like a always block, similar to always block. That's why the name monitor, because we are monitoring the change. Display means just display the output. Okay, so monitor, what does monitor do is, monitor is like it will track whatever signals are present. What do I mean by it? So here, right, I have these signals except time. Obviously time will always change, except time. Okay, except time, it will track a, b, sum, all this it will track. Okay, if a, b or sum, any of these change, right, at any point of time, this monitor statement will again print the output at the terminal. Okay, this one you have to know. So here I have given an example, right? So this is the example, reg clock and reset are there, initial, begin, monitor, time, and this, and the clock, what I am doing to the clock, after every 5, like same thing, right? What I think we have, you done this same example previously. So always the clock is like changing, always delay 5, clock is not clock, and I have obviously initialized clock to some value. Okay, so delay 5 should be there, delay 5. Okay, so as the clock value is changing, then this monitor statement will again run. Okay, so or if clock value doesn't change, reset value changes, then also this monitor statement will run. Okay, so you can observe after every 5 seconds, as the clock value is changing, the monitor statement, although I have written the monitor statement only once, but it will print it thrice. Why? Because inside this, right, I have clock and reset as its signal, and even if one of the signal changes, it will print again, it will execute this statement again. Okay, so that is the advantage of monitor, because we want monitor because we want to monitor the simulation and outputs of the different variables, so that we check that everything is working correctly or not. Also there is one more thing known as monitor on and monitor off. So if you anywhere write $monitor1, that means it turns the monitoring back on. It will display the statements. If you press monitor off, it will not monitor. It will not monitor any change. Okay, it will not monitor any change. So these are only for debug purpose, and like we generally don't use this. Mainly we will use monitor. Okay, so remember, only one monitor task can be active at a time in the simulation. Okay, at the same time of the simulation, only one monitor task can be active. So yeah, that is about the monitor and display. So like this is the difference between monitor and display. So execution, it executes only once when the statement is hit, continuously updates whether a monitor signal has changed or not. Use case, print one time message or logs monitor signal changes during the simulation. It adds a new line, it also adds a new line. Like if I have a display statement here, okay, like this is a like one of the display statement, display hello. Okay, and then again I have another display statement. So in C, right, what happens if you don't add a new line, it will not add a new line. But here, hello Verilog, here what will happen is automatically Verilog understands that I'm writing a new display statement, so automatically it will add like this. After this, right, it will add a line, so it will, this will be printed in the next line. So in C what happens, like in Verilog what will happen, this will be hello and this will be Verilog, one extra line will be added. But in C what will happen, it will come as hello Verilog. There will be no space, nothing. Okay, unless I use some placeholders here, something, some escape characters, it will not provide any enter. So that is the difference between C and Verilog. Okay, so that's why it is telling that it automatically adds a new line. So that was about the display statement. So few like illegal operations of display statement can be there. One of them is this one, that you have written value of a is this, then you have given a signal, but you have not given a format specifier or a placeholder. Okay, so for these are known as format specifier as well. So you have to provide a percentage d or anything, right, to show the output. If you don't provide a placeholder, it will not understand where to put this variable, where, in which area, which place, right? So that's why this is wrong. Correct one is we have to put a placeholder or format specifier. Okay, or if you here write here at time %0 $time. Okay, always include $time. So like let's say if you don't include this $time, right, then it will not include the time. So you have to include the percentage time. It is included here actually. So like for debugging purpose, like generally we like you may have forgotten to print the times, but for debugging purpose you should always put the time. That's why that is what is written over here. That's why the time is here. Like that will be helpful for you, because later at a later stage you might want to know like whether at this point of time I'm expecting this output from this signal or not. Okay, that's why it is generally recommended to put time in your display statement. Okay, that is the recommendation. Then wrong format specifier. So like if your data, right, is not a number integer, it is like a string or something, and you try to do %d, then it will throw out an error. Okay, because there is a mismatch, right? Data is a string, you're trying to display output as a binary. You can display output as a binary, it will just show it a ASCII code. Okay, so although it will not show you a syntax error, but that is a logical error, right? And you should ignore those things. Okay, so that is one thing about the format specifier. The format specifier must match. You should always try to put simulation time. These are all good, like good practice to follow. Okay, and of course don't forget the format specifier. Why I have to write the format specifier? That will be replaced with the value of the signal. Okay, now let's come to another data type, okay, named as register. Because reg I have already explained, but inside reg there are many more types, data types. Okay, reg is a Verilog. Registers in Verilog are variables that retain their value until explicitly updated. It's just like variables in software. Okay, just like variables in C. Okay, just like variables in C. Okay, they do not directly correspond to hardware registers, flip-flops. They do not directly correspond to hardware registers, flip-flops, unless used in procedural blocks with clocking events. Okay, So like they are not actually flip-flops unless they are used in procedural blocks like flip-flops. But specifically they do not correspond to hardware blocks, and that's why they will retain their value until explicitly updated. That means they don't need a continuous driver. Okay, they will not need a continuous driver. So that is the difference between like net and register. So here, right, net required a continuous driver because it was continuously, it has to be like, it is just a wire, it has to get pulled down, pulled up to some value. Okay, but registers are just like Verilog, they don't need continuous driver. That's why they're different. Okay, they're different than this nets. Okay, that is the main difference between registers and nets. So the purpose of register are generally used to store data or state. They retain their value until another value is explicitly assigned to them. It is declared with the reg keyword, and this is 3:0. I will explain about this. This is a 4-bit register. What does this 3 and 0 mean? Just in the next few slides or just in the next lecture I will explain this. Okay, for now just understand this is the MSB, this is the LSB. So it has 4 bits starting from 0 to 3. That's it. That is the just what I wanted to explain to you. Default value of register is X unknown. Okay, default value of wires are high impedance. Scope can be used inside procedural blocks, that is initial always. Okay, cannot be driven by continuous assignments like assign, right? It cannot be used in assign statements. Okay, important point to note here. Okay, so this is basically known as the width of register. So it is of width 4, like it has 4 bits, that's why width of the register. It has multiple bits, right? So same thing is written here. Like this is the basic type that we have been learning till now. There are other types as well. I will explain that. Basic reg type can store binary value, this 1, 0, X or Z. Okay. Now we have another data type known as integer. So integer is basically what? A 32-bit signed integer. Okay. Signed means it will have positive and negative sign. So integer, as the name suggests, it is also a rich data type, but it is integer. We cannot store floating numbers. Floating numbers means any 0.32 or something like that. It will only store integers. Okay, so it is generally used in loop counters or arithmetic operations. We will use this, there we will understand. Okay, so I'll come to this register example later on. Real is used to represent real numbers like full floating point numbers and all those things. It is not synthesizable. Very important, it is not synthesizable. Integers, although you can synthesize them somehow, but floating point numbers are not synthesizable in hardware. Okay, so like let's say temperature is a real number, right, because it has floating point numbers. Okay, so it will be 37.5. We can represent it in floating number. So I have forgotten the length, what is the exact length of this, but like there is some way. I think this stores in IEEE floating point representation, if I don't forget this totally. Okay, if you have studied COA from me, then you will understand. Okay, so then we have time. Time is another reg data type only. So it is a 64-bit unsigned integer. Unsigned, why? Because time always will be greater than 0. Okay, that's why it is unsigned, used to represent simulation time. Okay, so I can store this time t, I can store this t equals to dollar time plus 1 or something. So it can store the time data type. Time has its own data type. Why? Because time will always be positive, so it has to be defined, right? So that's why it has its own data type. It is positive always, and time here time data type is 64-bit unsigned integer. So this I will come to the code, don't worry about it. Okay, so like few things are there. So okay, let me come to the code only, then I will discuss about these things. Okay, let me go to the code, then I will discuss about these things. So if I just turn on the VS code, okay, still the VS code is not showing. Okay, so let me show the VS code. Yeah, so this is the registers. So let me open the test bench as well. So the test bench is open. Okay, fine. Time example, we have to use other example as well. Okay, first list. Okay, let's show you the simple register first. So this MUT module in the test. This one I will comment out because I'm not using it. Okay, so this one is here. Yeah, so that is it basically. So like this code, I hope you understand. Like just simple reg is there. I'm like initializing reg with 1, then after 100 time units I'm initializing it with 0. Okay, so this one is a signed integer, this one is not that important to me, this is just an integer. Okay, so these are just examples. So like this, if I just execute, right, so for me to execute, first of all I have to do cd to my current project directory. The file has changed, so I will do cd to my current project directory. Then I have to do iVerilog and name of the VBB file and the and the testbench file, right? So this is registers dot VBP, then registers testbench dot v. Okay, I will press enter. Okay, there is one syntax error in the testbench. Okay, what is gone wrong? Line 17. Okay, begin and is there. Okay, I have forgotten to put a semicolon, so this kind of silly mistakes will happen. So first I will do iVerilog registers testbench and to the name as registers VBP. Then I will call this registers VBP. Now the VCD file has been opened, although I am not printing anything, but I have few variables, right? So I can show those variables on the GTK wave. GTK wave registers VCD. Okay, if I open this now, I will show you the GTK wave. Just give me a second. It should be shown. Yeah, now it is showing. So now if I go into the register testbench, if I have a module under test, it has a register named reg. It should have one more variable, right? Why it doesn't? Okay, it has reset only. Yeah, it has reset only. So if I show you the reg, so at 100 seconds, right, it is going to 0. So at 100 seconds only, I am ending my simulation because I have not mentioned when I am ending my simulation. So now if I say here that after 200 seconds okay, you cannot see the code, so let me just quickly turn this off. After 200 seconds I want to finish my simulation. Okay, so it will finish after 200. It finishes automatically after 100 because after 100 nothing changes, so compiler automatically understands that, but user wants to finish after 200, so now it will finish after 200. Okay, so that is what it will do. So let me exit from the GTK wave first. Okay, and let me recompile this again. So if I recompile this and do VBP, then now it says the simulation has finished after 200 nanoseconds. So now if I open the GTK wave, okay, and if I show you the waveform, okay, not my face, yeah. So now if we move into the register MUT, we have a reset signal. Now you can see, right, the simulation has finished after 200 nanoseconds. So like that is the use case of finish simulation. Okay, so now you see the how the register is changing from 0 to 1. That is a simple register that I have already explained. Like this is not like that difficult example. Now let's come to next example. Okay, so so this is a signed integer. So now if I try to write like this integer, right, always should be used inside a always or initial block. So if I use initial, not integer, sorry, any register assignment should always be inside initial or always block. Okay, initial, and I'm just writing a single line of code, so it will not make any difference. I10. Okay, so if I write I10 and then if I simulate this one here, just I've changed the let me do it one thing. Let me do it here. Okay, separate, make it separate. That will be better. MUT. Okay, now let's call this function again. Recompile it. Okay, so VBP has been done. Now if I want to see the waveforms, okay, so these are the waveforms. Now if I go into the integer I, you can see the integer I, right, has 10 value. Okay, but what is the problem? The problem is, let's say if I want to store a floating point value here, will it let me store it? Okay, so if I store, like, let me store a negative number -10. Okay, So will it let me store the negative number? Now if I compile it, it shows here, it should show here the value -10. It is showing -10. Okay, no problem. Now if I want to store here value 10 minus 10.1, will it allow me that? So let me compile it again. So it allows -10.1, but it will not store that -10.1, right? It will store a like integer. So what it will do, it will truncate. So I will just show you the output. So you can see it just truncated, right? It didn't store the 0.1, it truncated. So it will truncate. So now if I store, let's say if I store 10.9, okay, will it store 11 or -10? Will it store -11 or -10? So now what it will do, it will just like store the nearest integer, right? So it will store -11. So if I compile it and do the VVP and then again see the output, it will just store the nearest integer. So nearest integer to this is -11. So let's say like this is plus 10.9, same thing will happen, it will store plus 11. Okay, it just stores the nearest 11, nearest number. Okay, so I hope you have understood the difference between integer and signed. Also it can store, there is no problem with storing signed integers. Okay, so let me comment it out. Let me uncomment this one. Okay, so this is a register example, like you can like automatically see the register example. Okay, so let me comment this one out. Let me call this function registers example. Okay, so there will be display statements now, so it will be easier for you to understand. Okay, so without the GTK waveform, I can directly show you this iVerilog and VVP. So now you can see like this, right? A space is coming. This space is coming. We can remove this space with properly using the format specifier. So if I write here 0, right, it says me that don't provide any space, 0 space. Okay, if I write here 0, it will tell no space has been provided. Okay, so now if I try to compile it again, and it will print it without space. You can see previously I had a bit of space here, but now I don't have any space. Okay, so that is the advantage. Basically, I hope you understood. Like real number has floating point numbers, counter has integer value, simulation time can be used to store time value. Okay, so this is the example, and these are the print statements and all those things. Okay, so again you see, if I'm having a delay of 10, then again I am storing the simulation time with the value time. It stores the value 10. Okay, why? Because this is after 10 units of delay, and this, right, $time assigns the current time. Current time is after delay, adding delay of 10 is 10. So that's why the output is 10 here. Okay, so I hope you have understood this one. This one is pretty easy. Okay, so now I will tell you the integer example. Okay, show you the integer example, although like these are all shown only, not that difficult. So let me give it a space here, way better. So let me copy this integer example. Okay, so this, right, if I recompile it, it is getting compiled, right? So what am I doing here? So first I am declaring a variable counter integer type. Okay, then I'm displaying the value of counter after 2 units of delay. So nothing, currently I have not changed anything to the counter, that's why it displays x. So the as we know, default value of reg is x, that's why it is also a reg data type, so it will give me x at time. Current time is 2, that's why time 2. Now this, all this, right, will execute parallelly. So again this one will also execute after 5 units of delay from 0. So this executes at time 5, and of course I have assigned the value -1, so we are seeing -1. Okay, then what I'm doing, I'm adding 32-bit number, which is totally valid because integer is a 32-bit number, right? It is a 32-bit number, so it can store 32-bit numbers. So I'm adding 15 and 10. So it should provide me 25, which is I'm getting 25 at 25 only. Okay, at at 5 units of time only, because inside initial block everything happens sequentially. So first this one has happened, this one has happened, but there is no delay, right? I have not added any time delay. So after that this one will happen without any delay, then again this one will happen, and then after that we will finish. So if I write finish here, right, that means it will complete all these statements, it will complete, then we will do finish, then automatically it will finish the simulation. Okay, all these statements after completing all the statements. So basic example of integer, nothing serious. Now real number. Okay, so let's check example of real, because I have told you real data type also we have. So if I show you a real data type example, okay, multi, okay, so now if I see that I have a real variable delta. Okay, so initially delta has value, should have value 0. Okay, so like real variable, right, initial value of real variables is actually 0. So I forgot to tell you that although it is a reg data type, only this has a bit of difference, that initial value of reg data type is 0. Okay, that is the difference. This I have written in my notes as well, I will point at that out. Initial value of reg data type is 0. Okay, so I will write here initial value, not reg, sorry, real data type, initial value of real data type is 0. Okay, you should be mindful of this. Okay, so that's why delta is shown here as 0.00, okay, as it is a real data type. Okay, then I am storing delta to be 325.14, which is exactly showing here up until, like, it has some precision, so it shows up until how many digits after point 1 2 3 4 5 6 6 digits after point. Okay, so this is what it is showing here. Okay, so delta is not equals to 300. Okay, this should be 325. Yeah, so now if I store like this, look, this is like scientific notation, if you know this, right, 1.23 e raised to power 4, that means basically 1.23 into 10 raised to power 4, that is what this means, right, and exactly that is what is happening over here. So 10 raised to power 4 is 12300, so that is what it is showing. So we can use scientific notation in delta, sometimes we have to use scientific notation, that's why we can use scientific notation in delta. Okay, so when showing delta in scientific notation is this. Okay, then obviously I told you, right, this is a integer. So if I store this integer with a real value, it will simply convert it to an integer, to the nearest integer, right, greatest integer function, to the nearest integer, not the greatest integer function, sorry, to the nearest integer. Okay, so it will round off the delta assigned value to the nearest integer, to the nearest integer. So as this is like, this is already integer, but I can store this one, right, this is already integer, right, 12300, this is already integer, so I can store here, that would be better, 3 to 5. So now if I compile this, you see it is storing it to the nearest integer. Okay, so this was about the real example, real numbers example. Now let's come to the time example. Okay, so if I come to the time example, again, if I rerun, like, what is this doing? First I am displaying the sim time. Okay, the sim time is of time variable, and if nothing is stored in the sim time, then let's see what is the default value of time data type. So if I just run this code, so the default value of sim time as well is x. So remember, only real data type has default value of 0, except that all the other rich data types have real have default value as x. Okay, so that you have to remember. I will write this point in my notes as well, okay, later on. So after this, what happens? Again, I do initial beginning statement. I assign the current time after a delay of 5. I assign the current time to the safe sim time. So the safe sim time has the value 5. Again, after 10 more delay, I assign the current time. So now it will be 5 plus 10, because 5 delay has been added, another 10 delay has been added. So total 15 will be displayed. Okay, so here 15 is displayed. That's it. Like, this is a very basic thing, very simple thing. I don't feel like we have to go in too much in depth here. Okay, so yeah, let me come back to our notes. So here, right, just wanted to explain this at the end, that here I wanted to explain this, that my real data type will have a value of 0, will have a default value, will have a default initial value, will have a default initial value of 0.0. Okay, except that all others will be x. Okay, this much information is enough. So like whatever I've explained, right, that is what is written over here. Integer has default value as x, and how we're using the display, all those things. Real has default value as 0. Its use case is representing floating point numbers, like this is how we have used it. And time has default value as x. Again, it is a 64-bit number. Okay, it is used to store the simulation time. So these are few like difference between reg and integers. So reg is unsigned by default. It is unsigned. Like basically unsigned means it is, there is no sign, that means it is positive. Okay, it can only store positive numbers. Reg cannot store negative numbers. Okay, it supports bit manipulation. We will understand what is bit manipulation. Integer is signed by default. It is signed by default. That means it can store both positive and negative numbers. It is generally used in counters or loop. We will see the use case later on. Real versus integer. So real supports floating point numbers. Conversion to integer truncates or rounds to the real number. Okay, rounds the real number basically. So rounds to the nearest integer. Okay, time variable used exclusively for storing the simulation time tracking. Okay, this is not used for synthesis because time variable does not exist in synthesis. Reg is used for flip-flop modeling. Storage integer is used for looping counters. It is used for like simulation of floating point computations, and time is used for capturing the time. Okay, so that's basically it for this lecture. In the next lecture, we'll learn about vectors, arrays, and obviously I will give you few homeworks to what is it, to the assignment problems. Whatever we learned till now, right, I'll give you homeworks to all of those things. Okay, so I hope you have enjoyed this lecture. If you did, do make sure to hit the like button, and I will see you in the next lecture. Until then, happy learning.